All right, just a reminder that we will have a quiz on Monday, and your sapling's due on Monday, so try to get started on that earlier. That way, if you have questions, you can always email me or stop by my office. All right, so yesterday we talked about selecting an appropriate base. We said you've got two competing acids present in equilibrium. Therefore, the stronger acid should push the equilibrium in the direction you want it to go, right? In this case, we said our conjugate acid for our base should have a pKa much higher than the acid that we're trying to deprotonate. And we saw an example of that down here. And we saw an example of how some common bases like hydroxide just aren't good enough to deprotonate organic molecules. So in the bottom example, we said the pKa of water is 15.7. Water in this case is now more acidic. That means the equilibrium is going to favor starting materials, not the deprotonated thing we want to get. Okay, and then I give you the common organic bases along with their corresponding conjugate acids. There's a handful of tables out here. This one I just selected because it's the most common bases that you'll run into. Yep.
On the backside, the solvents, they also have the pKa value, so could you technically use a solvent as acid?
So the question was about solvents. That's what we're going to get into today. Okay. But we have to be very careful with solvents because we don't normally want a solvent to participate in a reaction. It's just the medium that the reaction takes place in. Okay. Yep. Do you have a hand up? No. Oh, okay. You're looking at your watch. All right. If you notice too, I've classified these by weak bases and strong bases. In general, the term weak and strong is a nebulous gray area. This is something we have to be very aware of as chemists. We have to use pKa values as much as possible if we want to be precise. All right, so we saw an example yesterday, but what we need to do today is kind of switch gears, and we're going to look at the solvent systems that we're going to be using. So selecting an appropriate solvent for an acid-base reaction. So like I previously said, a solvent normally doesn't participate in the reaction. In a reaction. On rare occasions, it does, but what I mean by this is normally we're not going to be making and breaking bonds with our solvent, right? The solvent's just there. That just means that the solvent is the reaction medium. Oftentimes, what we do is we choose a solvent that's most appropriate because we need to A, dissolve everything in there, and B, sometimes the solvent stabilizes things and allows the reaction to occur, and we'll see that later in the term. Yeah?
You ever consider the solvent a spectator, or no, because it does not work?
Yeah, so the question was, do you consider solvent a spectator? Yeah, essentially it is a spectator. It's just kind of hanging out, helping to dissolve things for the most part. All right, so let's take a look at an example reaction. All right, in this example reaction, I'm going to have acetone. Acetone only has one type of proton coming off of it, meaning the methyl groups on each side, the CH3 groups. All of those protons are equivalent. I'll just show one side, and I'll say, okay, each of these protons I'll label as red. And if you look this up in a pKa table, the pKa of acetone's protons is about 19, give or take. All right, if we go back and we want to select an appropriate base, maybe I'm going to pick sodium amide, which is NH2 minus. And in this reaction, we could imagine, hey, this base could theoretically grab this proton, clamp down, and we could get a carbon with a negative charge. Is there anything else stabilizing this conjugate base? Resonance, right? So we could draw the resonance structure for this if we wanted to. So maybe I'll do that right below. Say, hey, this does have resonance stabilization. Just to practice, we'll draw this in. And this is a common anion referred to as an enolate. So a resonance stabilized negative charge getting kicked up to an oxygen on a carbonyl. All right. And then if we think about this too in terms of our conjugate acid in this case is going to be ammonia. The pKa of this is going to be about 38. So is this deprotonation event going to be favorable? Yes, absolutely. So if we look at this, though, we could say, well, we've got a reagent. The reagent and the starting acid are typically put into a solvent anytime you're doing a chemical reaction. So let's pick the universal solvent. And I'll say, all right, let's just run this reaction in water. And I'll even color code this as blue. And we'll just say, what if this is our solvent? All right, so then the question is, will this reaction work?
No.
Why? Okay, the pKa of water, in this case it's our solvent, is 15.7. What's the problem then? Water is more acidic than the thing we're trying to deprotonate. It's going to get deprotonated before acetone ever gets protonated. So let's make a note of this. Water, our solvent, is more acidic, therefore it will get deprotonated. Essentially, this acid-base reaction will not occur. So I'll just go ahead and write, this will not occur. Just put a big X through that. All right, so now the question is, all right, we need to pick a solvent that has a higher pKa, right? So if you go ahead and look at that handout that I gave you, I've got a bunch of organic solvents that are commonly used in a lab setting. And I've classified them by a variety of different categories. The first ones are called polar protic. So I've got ethanol, methanol, and water. What do you notice about all of these? They're about the same pKa. And what special intermolecular force do they have? H bonding. Okay, so these can H bond. Okay, polar aprotic. If we look at these ones, they're polar molecules that cannot H bond, right? None of the hydrogens in these polar aprotic molecules are coming off of fluorine, oxygen, or nitrogen, but they're still very polar. And then down on the bottom, we have nonpolar compounds. So not only can they not H bond, but they have no significant net dipole associated with them. They might have a small net dipole, but nothing on the range of our polar protic or polar aprotic compounds. So sometimes we'll choose different solvents based on whether or not the reaction's favored in solvent that's polar or nonpolar, and we'll talk about that more when we get into reactions in second term. All right, so let's pick a solvent that might work better for this reaction. Okay, so then we could say, well, maybe we're going to run this in, what might work? Acetonitrile, sure, why not? We'll say acetonitrile. Okay, so maybe we can just take this whole reaction. I'll use my power of the lasso tool. Copy it down. Cowboy Jeff. You can just copy over your notes. I know. Lasso everything. All right. So let's do acetonitrile. If you think about it too, acetonitrile has how many carbons in it? One. Somebody was asking me about this. It's important to remember that this spot right there is a carbon, right? So the part where the line meets that triple bond is an assumed carbon. And then out here we have a second carbon. So it's two carbons. Another way of drawing this, if you just want to draw out all of your bonds, would be like this, right? So make sure that you are aware with triple bonds that that is present. So let me fix this again and say, all right, this is acetonitrile now. Now this is my solvent for the reaction. We're no longer going to use water. So I'll color code this for my solvent. Come on. Either way, I'll just box it. There we go. So this is my solvent now. What was the pKa of acetonitrile? 25. All right, in this case, the reaction will work. What's going to happen to the solvent in this reaction? It's just going to hang out. It's going to do its own thing, kind of watch the reaction take place, which is good. We don't want our solvent to participate in this reaction. We don't want it to do acid-base chemistry. So we do have to be pretty prudent anytime we're selecting a solvent. Does that make sense? All right. So let's make a note. This reaction is favorable since the solvent won't be deprotonated. Okay, I'll show you another common trick that organic chemists use. And this one's going to be a bit different. We're going to start out with not acetone, but this compound called acetyl-acetone. So it's a diketone, right? 2 ketones in one molecule. Where's the most acidic proton going to be? In the middle, right? We saw in our problem of the day that if we deprotonate one of these 2 protons, we have a structure that is doubly resonance stabilized, right? That's good. All right, so I'm just going to pick a base. I'm going to pick sodium amide again. I'm not going to show my spectator cation, but we can show our arrow pushing, and we can say, all right, I'm going to grab this. Or actually, sorry, I'm going to change this base. We'll make it easier. Let's do hydroxide. I apologize. But same idea, right? Hydroxide, in this case, we can imagine deprotonating one of those. And in this case, we're going to try to find a solvent to put into that blue box. We can show our equilibrium arrows. I'm not going to bother drawing the resonance structures for this one, but you get the idea. And in this case, water is going to be our conjugate acid, and we want our solvent to basically just be hanging out during the reaction. All right, first thing I would always do is double check that my base was good enough. So if I go to the pKa table and look for this diketone, let's go ahead and do that. I've got a ketone here. If you notice on top of the ketone side, it has a little X group dangling off. It's saying what's in that X position. So the first option is, well, what if it's just a hydrogen? That's not what we're looking at. What if it's a phenyl group? Not looking at that. What if it's a sulfur? Not looking at that. All right, what if it's a COCH3? In that case, that's exactly what we're looking for. So in this case, we're looking at something that has a pKa of 9, right? So let's go ahead and plug that in and say pKa of this is going to be about 9. All right, if we think about our conjugate acid over here, what's the pKa? 15. pKa is 15. 15.7 if you want to be precise. All right, looks like it's checking out, right? We're over 5 orders of magnitude difference, so that's definitely favorable. Now we've got to pick a solvent. Should our solvent pKa be higher or lower than 9? Higher. Okay. But what if I just want to make my life easy and I don't want to throw anything new in this reaction? What if I just run this reaction in water? Water is cheap, cheapest solvent available to us. Will this work? Well, let's think about it, right? pKa of this is 15.7. Is our solvent more acidic than our starting acid? No, it doesn't matter. Our base is still going to go after the most acidic proton, which is right in the middle there, like we're showing with our arrows. So in this case, water is not only our solvent, but it's our conjugate acid. As a chemist, I like this. This is fewer steps of purifying my product. I don't have to get rid of my solvent because it's the same as my conjugate acid. So in this case, oftentimes we choose a solvent that is the same as our conjugate acid. Does that make sense? It just makes life a lot easier for chemists. It does look a little bit weird when you're looking at it. So let's say trick. Chemists often choose a solvent that is the same as the conjugate acid. And just to clarify, I'll write that this is my solvent for the reaction. Does that make sense? Yeah.
So would that mess with equilibrium at all, or no, because the pKa's are far enough apart that it's essentially going to drive it forward?
Yeah, so the question was about whether or not water will mess with the equilibrium. Not really, because we're greater than 5 pKa difference, or 5 pKa units apart, it's going to favor the product side no matter what. Yeah. We'll talk more about kinetics later. Basicity, we're looking at thermodynamics, not reaction rate necessarily. That's something entirely different, but we'll talk about that later. Yeah.
When you're treating the solvent, it has to be greater than the acid, but then does it have to be less than the pKa that conjugate acid?
So the question was, your solvent pKa needs to be higher than your starting acid for sure. But what about its relationship to the conjugate acid? It doesn't matter as much. You just want to make sure that it's not getting deprotonated before your acid is. Yeah. All right. So let's continue on. We've talked almost exclusively so far about Bronsted-Lowry acid-base theory. What was the other acid-base theory? Lewis. He often gets overlooked, didn't get his Nobel Prize. All right, so let's talk about his acid-base theory. All right, how did he define acids? Who remembers? Electrons. Do Lewis acids donate electrons or accept electrons? Accept. So they accept electrons. Bases are the opposite. They donate electrons. And if we think about Lewis acid-base theory as being in this field of knowledge, right? A little nugget of this, or some subset of this, will still be Bronsted. So really, Lewis acid-base theory is much, much bigger. It's all-encompassing, but it includes Bronsted-Lowry acids and bases, and I'll show you why. Okay, so let's say we're looking at a typical Bronsted-Lowry acid-base reaction. And in this reaction, I've got my acid with some proton attached to it, and I've got some generic base B, and we've got this equilibrium situation occurring. Let's think about this. Okay, our base is going to steal this proton from the acid. We'll get our conjugate base plus our conjugate acid. Pretty simple, right? This is what we've been doing all week. All right, now let's focus on the starting material side. What's donating electrons? Well, where are the electrons coming from? The base, right? The base is donating its electrons to that proton, right? So we can think about it that way. We can say, okay, this is our base. It donates its electrons to the proton, right? Therefore, it is also a Lewis base. Makes sense, right? Conversely, over here, we've got our acid. And if we think about A, right? A was the center atom that our proton was coming off of. It ends up receiving electrons, right? Okay, so an acid accepts electrons from the base. Therefore, this is also considered a Lewis acid. Makes sense, right? So Bronsted acids are also Lewis acids. Bronsted bases are also Lewis bases. Yep.
Doesn't, like, technically the hydrogen also donate and accept electrons at the same time? Because the hydrogen is like losing the electrons to the acid and accepting the hydrogen.
So the question was about the proton itself. Think about the entire molecule, right? So in this case, the base is donating its lone pairs, right? So that immediately means it's an electron donor or a Lewis base. The acid as an entire molecule is accepting electrons from that base as an entire molecule, therefore it's a Lewis acid. So think about it more in terms of the whole molecule, not individual bonds, I should say. Yeah, good question though. All right, so it is confusing. People oftentimes overlook this fact and they think, no, Lewis acids and bases are entirely different. Not true. Bronsted acids, Bronsted bases are also Lewis acids and Lewis bases. However, the opposite's not true. So now we got to go down the rabbit hole a bit. All right, let's try another one. So not all Lewis acids and bases are Bronsted acids and bases. How do we define a Bronsted acid and base? Well, we said that involves movement of protons. So maybe there's some acid-base chemistry where we don't move protons around. And there's a few classic examples of this. Let's consider ammonia plus BH3. This is borane. This is actually an acid-base reaction, and let's try to figure out what's going on here. All right, so think about NH3. What's the hybridization of nitrogen? It's sp3, right? So we can look at this one and we can say this is sp3. Let's try to draw this using a picture. All right, so what shape is it going to be? Electronically, it's going to be tetrahedral, but what about its overall shape? Trigonal pyramidal, excuse me. So we'd have one hydrogen down like this, one hydrogen kind of down like this. They're almost going to be like bar stool legs. And we've got our lone pair kind of hanging out in this cloud up here. Make sense? So classic Vesper theory, we've drawn ammonia. All right, let's think about BH3. What's BH3's hybridization? sp2, okay? So let's go ahead and write that down. And again, let's draw this. So we've got boron in the center. Got a hydrogen going back. I'm going to imagine this laying on its side. Looks like this. All right. So each of these bonds is going to be an sp2 lobe, right? What am I kind of omitting though? A p orbital that was unhybridized. Okay, so we've got this unhybridized p orbital, so I'm just going to go ahead and draw this. So this is an empty p orbital. Makes sense? All right. Looking at this one, which one do you think is going to be the electron donor? The one with lone pairs, the one with electrons to donate. Okay, so we can immediately say, hey, this can dump its electrons into that empty p orbital over there. We saw earlier on in one of our earlier pods that borane is a good Lewis acid because it has an empty p orbital and it doesn't have an octet of electrons. So this is kind of best case scenario for a Lewis acid. You can draw this using just traditional arrow pushing like that. You're not moving a proton though, right? All we're doing is dumping electrons down. Okay, so now let's consider what the product might look like. So down here, I'll draw my equilibrium arrows. And the nitrogen, in order to dock with that empty p orbital, we can imagine it kind of flipping around. So we're going to have a new nitrogen-boron bond. The nitrogen still has 3 hydrogens coming off of it. Like that. The boron still has 3 hydrogens coming off of it. So I'll draw it like this. All right. Am I done? Formal charges. All right. Nitrogen should have what formal charge? Positive. Boron would have what charge? Negative. All right. What do we call a molecule that has both positive and negative? Zwitter ion. All right. The net charge of this is still 0, right? All right. Now my second question. We could draw this up above. So let's just, for the sake of clarity, do this. We've got a negative and a positive. What's the hybridization of nitrogen? So this nitrogen right there, still sp3. All right, what about the hybridization of boron? sp3. So during this Lewis acid-base reaction, we actually changed the hybridization of the boron, and we know this due to Vesper theory. It doesn't want to be sp2 anymore. It wants to orient all of its lobes so that they're far apart from one another. All right, what this is referred to as is an acid-base adduct. So let's make some notes down here. We said that this is going to be our Lewis base because it's donating electrons. This is going to be our Lewis acid because it is accepting electrons. And then this is going to be our Lewis acid base adduct. This molecule on the right that I've shown is called Ammonia-borane. It's actually under a lot of investigation for potential hydrogen storage applications. If you've read about hydrogen cars at all, what's the problem with hydrogen cars? You have to have a super high pressured tank. It takes a lot of energy to pressurize a gas, so you're losing the economic side that way. Hydrogen as a fuel is a gas. Our entire world infrastructure is based off of liquid fuels. So they're trying to solve a lot of these using chemical hydrogen storage applications. But a really cool molecule here. Does that make sense? We didn't move any protons around. All we did was dump electrons. You might notice, though, that in order for this to work, you have to have an empty spot for electrons to go into. So some Lewis acids have unique molecular features. Quite often, they have an empty p orbital. Yep?
So is there any pKa value associated with this, or no?
That's a good question. So the question was, what about pKa values for Lewis acids and bases? pKa values are only for Bronsted acids and bases. They only refer to transfer of protons. There aren't any numbers for Lewis acids and bases. Yeah. Yep.
Is that the same as a coordinate covalent bond?
Coordinate covalent bond? I guess I would have to... Is that something you talked about in general chemistry? I would have to look that up. It's been quite a while since I've taken or taught general chemistry. I apologize. All right. So like I said, good Lewis acids often have some unique features. So good Lewis acids often have the following. The first one we said is an empty p orbital. All right, there are a variety of different subclasses of molecules that have empty p orbitals. The first one we said is that group with boron in it, right? So what column is that in? If we look at the periodic table. So main group 1, 2, main group 3. So we skip over the transition metals. All right. So any element that's in the main group 3 typically has an empty p orbital if it's neutral. So group 3 elements that are neutral. So let's take some examples of this. An example might be BH3. That's the one we just saw. Right below it, aluminum is a really good Lewis acid if it's neutral. So aluminum trichloride is another example. It has an empty p orbital. Things like that are really nice Lewis acids. All right, there's another super common one that we'll run into in organic chemistry, and that's carbocations. So 3 bonded carbon with a positive charge, right? So for example, if we think about this being a carbocation, we've got 3 bonds to it, we've got a positive charge. That means it has an empty p orbital and is sp2. So carbocations are also really common. Either one of these has an empty p orbital, so they can accept electrons. All right. The second class is one you're probably more familiar with in general chemistry, and that's any metal with a positive charge. Just one second. Positively charged metals are great Lewis acids because they just want electrons. We're not going to talk about the bonds that can occur between metals, though. Yep.
So would the positively charged any group 4 work, or does it just not common as a carbon?
Yeah, so the question was any positively charged element in group 4. Yeah, that would work. However, carbon's the one we're going to run into 99% of the time. We really won't see silicon very much in this class. Any other questions? All right, so really quickly before we continue on, I did want to mention when I was grading the pods, a lot of people had incorrect arrow pushing, so I wanted to reiterate what's going on with our arrow pushing. So let's consider this acid-base reaction. Let's consider these electrons in the covalent bond as a pair, right? So there's always 2 electrons in a covalent bond. When this base grabs this proton, both of these electrons will pop over to that acid. So now our atom A has both of those covalent bond electrons. Now it's a lone pair just residing on A. And then over here, our proton is now covalently bonded to B through what used to be a lone pair. The key takeaway is remember that your arrow starts at your electron source. Our arrows don't show movement of protons. It is always used to show movement of electrons. So if we think about it over here, this is our electron source. It's our Lewis base. It's the thing giving electrons. So the arrow needs to start at those electrons, show where they're going. Don't show an arrow showing where your hydrogen's moving. That's not correct in organic chemistry. Does that make sense? It's a common way that people lose like a handful of points on their first exam is they just hurry, they forget to have their arrows going in the right direction. All right, so the last thing we're going to do today, I think we've got like 10 more minutes, is I've got a brief in-class activity. What I'll do is I'll post the key later tonight, but you're welcome to work with a classmate on this, either in class or through tomorrow, and then check your work on your own. Make sure you have full arrows, that you have the correct equilibrium arrows, and what I mean by that is, does the equilibrium go like this, meaning favoring products, or does it go like this and favor starting materials? So include the appropriate equilibrium arrows that you think you should have for that reaction. All right.